Okay, so let's end this lecture on an important, useful definition. I'll give you a couple of exercises so you can, get familiar with this new notion of complexity, this effective number of hypotheses, this growth function, and then I'll end with a combinatorial puzzle for you to, grind your teeth on. Okay, definition, to shatter. Okay, so remember that, if you have data points x1 to xn, so points x1, x2 up to xn, remember that, a dichotomy assigns plus or minus to each point. So there's plus, minus, let's say here's an example dichotomy, and we know that there are, 2 to the n different dichotomies. Okay, now you have a hypothesis set H, and, this hypothesis set consists of hypotheses, and each hypothesis induces a dichotomy, and we will say that H shatters. So H shatters the points if, H can implement all these dichotomies, all these 2 to the n dichotomies on this set of points x1 to xn. So H shatters x1 to xn if, H implements all 2 to the n dichotomies on x1 to xn. Okay, so that's the definition of shatter. It's nothing new. It's useful to have a term for the situation where a hypothesis set can implement all possible dichotomies on a particular set of points. And that means that with respect to those points, this hypothesis set is effectively as complex as you can get. Okay, now here are some exercises. So exercises. 1. Okay, supposing you have this hypothesis set and you have n points. So you have n points x1, x2 up to xn. So this is a specific set of n points that are shattered by H. Then show that m sub h of n is equal to 2 to the n. Okay. So this is nothing more than sort of carefully looking back at the definition of this growth function. This just says that H shatters a particular set of n points, in which case show that its growth function is 2 to the n. Okay. 2. Suppose you have a hypothesis set in some space, and suppose that m sub h of n is strictly less than 2 to the n. Okay. Then show that there's no set of n points, is no set of n points, x1 up to xn, that are shattered by H. Okay, so this is to show that, if the complexity measure for this hypothesis set is less than 2 to the n. So, in other words, it's not as complex as possible for sets of n points. It means that there's no set of n points that are shattered. And again, this is just, carefully parse and understand the definition of this growth function. Okay. Now, third exercise, a little bit less trivial, but still you should be able to do it. No problem. Okay. So, 3. Suppose m sub h of k is less than 2 to the k. So this means that, if you've shown this, it means that there's no set of points of size k which can be shattered by H. Okay. Then show that for any larger number of points, you cannot find a set of points that's shattered. So then show that m sub h of n is less than 2 to the n for all n greater equal to k. So in other words, if you find a value k, so a number of data points k, which breaks a hypothesis set. In other words, this hypothesis set is deficient with respect to that number of points. What that means is that, no matter how you choose those k points, the hypothesis set is not as complex as possible. It cannot implement all 2 to the k dichotomies. So if you've broken a hypothesis set at some value of k, at some number of data points, if k data points breaks the hypothesis set, then any larger number of data points will also break the hypothesis set and reveal its deficiencies. Okay, so think about these exercises. It'll help you sort of get more familiar with this brand new notion of the effective number of hypotheses, the complexity of a hypothesis set when viewed through the lens of a data set. Okay, and now for the combinatorial puzzle. Combinatorial puzzle. Okay, and it is a combinatorial puzzle, but I'll sort of phrase it in a way that makes it look familiar, at least with respect to this whole language of dichotomies. Okay. So imagine I have 3 data points: x1, x2, x3. Okay, and remember, a dichotomy assigns plus or minus to the data points. I'll use a visual representation of plus or minus that just makes it easier to sort of look at this picture. So here I'm classifying plus or minus for these data points, and here's how it's going to go. The empty data point is minus, and the filled data point is plus. So I'm going to say that this is minus, 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 plus. So I'll fill in plus, minus, plus, minus. So I'll fill in the plus. Okay. And minus, plus, plus. So I'll fill in plus, I'll fill in plus. Okay, so fine. Think of this as 4 dichotomies on these 3 points. If I wanted to, I could list out all 8. Okay, and if I listed out all 8, that those 8 dichotomies would basically, we would say that they shatter these points. Okay. But 4 dichotomies cannot shatter these points because you're not going to get all 8 ways to classify these points from just think of these as 4 hypotheses. But I'm just being more general. I'm just considering any dichotomies. Okay. Now, I want to point out, I want to sort of zoom in on these 2 data points, x2, x3. So let's zoom in here. Okay. Now observe that we have 4 dichotomies on x2, x3, and look, they're all different. Minus, 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 plus, plus, minus, plus, plus. They're all different. So we've managed, so these 3 dichotomies have managed to implement, so when you just view them restricted to these 2 data points, they have managed to implement all the 4 possible dichotomies on these 2 data points. So what we will say is that these 4 dichotomies shatter these 2 points. Okay. So these 4 dichotomies shatter x1, x2. And we don't care what they're doing on, shatter x2, x3. And we don't care what they're doing on x1. Okay. Well, I'm going to say that, if a pair of points is shattered, I don't like that. So I would like to find 4 dichotomies such that when you zoom in on any pair of points, when you zoom in on any 2 points, you will not find all 4 possible dichotomies for those 2 points. So in other words, no pair of points is shattered by my 4 dichotomies. And here we go. x1, x2, x3. So, I'll use the same visual notation. And look, if I put minus, 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 if I do minus, minus, plus, minus, plus, minus, and then plus, minus, minus. Okay. Now, consider any pair of points. Let's say x1, x2. Well, if I consider x1, x2, I have minus, 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 minus. So minus, minus is repeated. So there are only 3 different dichotomies if I'm only looking at x1, x2. So x1, x2 is not shattered. What about x2, x3? x2, x3 has minus, 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 minus. Okay, so x2, x3 is not shattered. What about x1, x3? Look at x1, x3. Minus, 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 minus. So x1, x3 is not shattered. There are only 3 different dichotomies that can be found when you just restrict yourself to any pair of points. And notice that all these dichotomies are distinct, yet they cannot shatter any pair of points. So these 4 dichotomies do not shatter any 2 points. Okay. And now the question is, can you make this list longer? Is there a longer list of different distinct dichotomies with which continue to have this property that no pair of points is shattered? Okay. Now you can work hard and try to see if you can find any 5 dichotomies for which no 2 points are shattered. You won't find it. So the answer is this is the maximum number of dichotomies that I could list, maximum number of distinct dichotomies that I could list for which no pair of points is is shattered. So this 4 is the max. Okay, I cannot list more, okay, but that's not the combinatorial puzzle. The combinatorial puzzle is to go up to 4 points. So suppose now we had 4 points, x1, x2, x3, x4. Okay, well, let's let me show you. I can list dichotomies in the same way. Okay, 1, 2, 3, whatever you want, dot, dot, dot. So you list dichotomies. For example, I can make this plus. Now I need a different dichotomy here, so maybe I'll make this plus and this plus, and maybe I'll make, these 3 plus. Okay. So I have a lot of flexibility now in how to pick my dichotomies, because when there are 4 points, I have 16 dichotomies to choose from. The question is, what's the largest list I can come up with? Okay, but I need to maintain the constraint that no pair of points is shattered. Okay. No pair of points is shattered. And that's a constraint, and that's what it's going to reduce me from 16 to something much less. The question is, what's the maximum you can find? Can you find 9? Can you find 8? Can you find 7? Can you find 6? Can you find 5? Okay, so what's the maximum you can find? What is the max you can find? So you can pause the video and try to find this. If you pause the video, I'll give you a second. If you pause the video, great. And if you answer that you can find 5, well, you've managed to match me. Okay, if you can find 6, you've managed to beat me. Okay, and so try to see what's the max that you can find, and we'll see you next time. So ciao.